Hello, we are the engineering group from STEM100, and our research project is called Muffled Miracles Investigation on Sound Muffling. Our members are Mike, Min, Sun, Nathaniel, and Kenneth. In our presentation today, we'll go over what experiments we have conducted and what conclusions we have drawn. Hopefully, by the end of this, we will have provided you with an in-depth representation of what materials we have found to muffle sound the best and which ones don't work so well.
To begin, our project focuses on experimenting with how different materials affect sound insulation. In today's urban environments, noise pollution is a growing problem. Understanding which materials work best is key to engineering quieter and more comfortable spaces. Our primary research question is, which materials are most effective at muffling sound? Our objective is to identify and compare common materials to see which provides the highest decibel reduction. We hypothesize that thick, soft, and fibrous materials with high porosity will reduce sound more effectively than thin, solid materials. For our variables, the independent variable, which is the thing we are changing, is the type of insulating material, such as cardboard, a pillow, or a towel. The dependent variable is the sound intensity level, which we measured in decibels. To keep the test fair, we kept several constants: the volume of the speaker, the distance to the microphone, the size of each material sample, and the room's background noise.
For this experiment, we used the following materials: a smartphone, a second smartphone or a laptop to be used as a microphone, a towel, a pillow, a piece of cardboard, and a ruler. We used one smartphone to play the noise, while the other device captured the decibel readings through a website decibel reader. The towels, pillows, and cardboards were our independent variables. We used the ruler to ensure an equal distance from the sound source to the microphone source.
We first getting started by getting a phone play a video on loop, then pause for the setup. We got the second device like a laptop or another phone, and we opened the decibel recorder website. To make sure it's accurate, we record the average room volume for 20 seconds to subtract the background from the final data. Then we position the recording microphone 1 foot away from the noise source, making sure everything was unobstructed, so the sound could travel freely. Finally, we resume the video and adjust the volume until the recorder hit approximately 17 decibel, after accounted for the room noise. Once again, ensuring the sound path were completely clear for the most precise result possible.
Next, we recorded 3 separate channels of unobstructed audio for 20 seconds each, making sure to stop and resume the sound between every trial to subtract the ambient room noise and maintain a target of 17 decibels. Once we had our baseline, we covered the phone with our first test material and repeated that 20-second recording process for 3 more trials, again subtracting the room noise and pausing between runs to keep the data clean. We then repeated these exact steps for every one of our independent variables, ensuring every single trial across all materials lasted roughly 20 seconds for consistency. To finish up, we took the results from those 3 trials for each variable and added them together to calculate an average for our final data set.
So this is a collective data chart of all our individual data. All of these numbers were averaged from our individual data. We were aiming to have an unmuffled sound of around 17 decibels, and you can see that we have the volume at around that range from 16 to 18 decibels unmuffled. Then we have boxes of each data entry for each member of our groups for each of the materials. This is a pretty formal representation of our data, so in order to aid comprehension of our results, we made a graph. This is a bar graph we have created in order to help visualize our data. As you can see, the y-axis is the decibels measured, the x-axis is the materials tested. Each bar represents a member of our group and their average decibel reading for that material. To simplify the data even more, we included another bar, which averaged all 5 data bars into one bar. You can see that's the green bar, resulting in the average decibels reading across all 5 members for each material. Although we tried our best to get our sound to be at around 17 decibels, we averaged out at 17.72 decibels collectively for the unmuted trials. After the towel was put on, that reading dropped to around 16.66 decibels. With the cardboard, that dropped to 15.6. However, the one thing that this graph really clearly shows is how well the pillow muffled the sound, averaging at 12.12 decibels, which would be around a 5 decibel reduction from the original unmuffled sound.
After gathering all the data, we noticed that the pillow came in first place as the most effective material to reduce sound. Cardboard came in second, ranking as the best second material, and the towel came in last with the least amount of sound being blocked. It just overall showed that the thicker and porous material reduced the amount of sound being passed through. For our conclusion, we decided that the pillow was the most effective overall to block out sound comparing to the other material that we test. This could be due to the fact that pillows are thick and filled with soft fiber, which help absorb sound wave. On the other hand, thinner materials such as towel and solid material like cardboard is allow more sound to pass through, which couldn't compete against the pillow. Altogether, this experiment data and have support our thesis of thick, soft, fibrous material with high porosity produce more decibels of sound than thin and solid material. Even without trying to minimize as many variables as much as possible, there are still several sources of experimental error. One of the major ones was room noise. While the room itself was relatively quiet, outside noises can cause inconsistent spikes in the recording and create an inaccurate baseline for our subtraction. Additionally, the location of the microphone has a large effect due to the nature of sound. Even slight deviation from the 12-inch measurement, it could result in measurement differences in data collected. Additionally, the method in which the material was positioned on top of the phone varies slightly. Towel draped loosely over the phone allow for sound to leak through the edge of the towel rather than only through it, thus affecting the measurement taken. In regard to the equipment, the free decibel meter online tool has not been calibrated, and various model of phone may have slightly different level of output from the speakers. Lastly, the manual timing of each 20-second trial is result a minor variation in when the trial began and ended, resulting in impact overall average. The potential sources of error indicate that our result can vary roughly by 1 or 2 decibel.
While our initial experiment provided a good foundation to begin research on this topic, there are many ways in which this research could continue. A simple first step in continuing this research would be to test additional materials such as foam, rubber, etc., and compare them to one another. Another aspect of research that could be tested would be to determine if the thickness of the material is important. For example, would doubling the number of layers double the level of sound suppression? An alternative approach to researching the topic would be to study the effects of varying sound frequencies. The research we conducted was based upon a single source of audio. However, low-frequency bass tones and higher-pitched sounds act differently, and certain materials may suppress one type of sound frequency much better than they do another. Additional research could include testing the effect of varying distances between the microphone and the materials, or layering multiple materials on top of one another to see if the combination provides greater sound suppression than any individual material. Finally, researchers could apply the findings from this research to design and construct a small soundproof enclosure and test the effectiveness of the materials within it. This would provide a direct link between the laboratory findings and practical applications. These are the sources that we use for our group research and presentation. Thank you for listening to our presentation today.